Okay, let's dive right into this. Welcome to today's explainer, where we're going to crack open the absolutely fascinating brain of Apache Spark to find out exactly what makes it tick. Now, if you've ever wondered how big data frameworks process literal mountains of information so quickly, well, you are in the exact right place. We are going to unpack the inner workings of Spark's query execution, and I promise you, the engineering behind this is just incredibly cool.
So, picture this. Imagine two engineers writing the exact same SQL query. Engineer A drops their code in and boom, the timer flashes green. It finishes in a lightning-fast 10 seconds. Meanwhile, Engineer B's exact same logical query drops in, but the timer just keeps spinning and spinning, crawling for 10 agonizing minutes. Same goal, wildly different results. Today we're going to uncover exactly why that happens. The secret weapon making that difference is the Catalyst Optimizer. Your raw SQL code drops right into this glowing central intelligence hub. Think of Catalyst as sitting squarely between your raw code and the actual cluster execution. It is literally the brain behind every fast Spark query, taking your human-readable instructions and translating them into the absolute most aggressive, lean, and efficient machine-level execution plan possible.
And this highlights a pretty foundational truth about modern data processing. Spark rarely executes your query exactly the way you wrote it. Actually, scratch that, it almost never does. Catalyst intercepts your code, analyzes it, completely rewrites it, surgically removes any unnecessary work you might have accidentally thrown in there, and builds an optimized execution plan long before the actual data processing even begins.
So, here is our roadmap for today's explainer. We'll track your query's journey through 5 steps. First, the need for speed. Then, the query's logical journey. Next, applying the optimization rules. After that, cost-based optimization. And finally, physical planning and execution. Let's get into it.
Section 1. The need for speed. Why query optimization actually matters.
Look, when you're processing billions of records across a distributed cluster, a single query can have dozens, sometimes hundreds, of possible execution paths. Choosing the wrong path isn't just about waiting a few extra seconds, right? It causes massive memory pressure, terrible network bottlenecks, and ultimately sky-high cloud bills. Catalyst's entire job is to navigate this maze for us and prevent those disastrously slow, expensive jobs.
Moving right along to Section 2, the query's logical journey, from code to plan.
Your query moves chronologically through 4 very distinct phases. First up, the parser builds an abstract syntax tree. Second, the analyzer steps in to resolve the logical plan. Third, the optimizer refines it. And finally, the planner creates the physical plan. At every single stop along this pipeline, Catalyst strips away inefficiencies and adds crucial execution context.
Now, if you ever want to peek behind the curtain yourself, you can use the explain extended command. It's basically an X-ray machine for Catalyst. Running this command lets you literally watch your query evolve through these exact stages step by step, transforming from a parsed plan all the way down to a physical execution plan. It's super handy.
Let's zoom in on that analyzer stage for a second. The analyzer takes your raw, unresolved code and consults the catalog. You can think of it like a strict librarian. It validates your tables, ensures the columns you're referencing actually exist, and double-checks your data types. It transforms unresolved attributes into a fully analyzed logical plan, which gives your query actual verifiable meaning within the database.
That brings us to Section 3, applying the optimization rules. This is where the real magic of Catalyst happens.
You see, Catalyst doesn't just run through its optimizations once and call it a day. No way. It uses a robust rule executor framework. Catalyst applies its optimization rules in batches, and it does so iteratively. It transforms the logical plan over and over again until it reaches a state where absolutely no more improvements can be made. We call this the fixed point iteration loop. Catalyst applies the rules, checks if the plan changed at all, and if it did, it loops right back around to reapply rules on the newly modified plan. The cycle just keeps spinning until it finally hits that fixed point, representing a state where the plan is as conceptually perfect as it can get.
So what kind of rules are we talking about here? Well, take predicate pushdown. This rule drops your filter conditions right down to the data source, so we read drastically less data from disk. Alongside it, we have projection pruning, which strips out all the unnecessary columns entirely from the scan. Combined, these two rules mean Spark brings dramatically less data into memory, saving us massive amounts of time and compute power.
And check out this rapid simplification.
This is a classic rule called constant folding. Instead of calculating 2 plus 3 for every single one of a billion rows during execution, Catalyst just precomputes it into 5 during the optimization phase. It simply swaps the expression out in the plan. It seems like a tiny tweak, right? But it literally saves millions of redundant calculations during runtime.
All right, Section 4, Cost-Based Optimization, or CBO, the math behind the magic.
While rule-based optimization is fantastic, it definitely has its limits. CBO abandons those simple logical rules and relies entirely on deep mathematical statistics gathered directly from your tables and columns. At the table level, it's looking at row counts and gigabyte sizes to estimate I/O. At the column level, it analyzes distinct counts, histograms, and nulls to predict exactly how many rows a given filter is going to return.
Using those rich, detailed statistics, Catalyst acts quite literally like a GPS routing system. It calculates the estimated computational cost of multiple different routes, say Plan A versus Plan B. It compares the CPU, memory, and network cost of doing a broadcast hash join against a sort merge join, and selects the absolute cheapest, fastest path to get the job done.
Which leads us directly into Section 5, Physical Planning and Execution, the final blueprint. This is the moment of truth, everyone. This is where the theoretical what to do, our beautifully optimized logical plan, transforms into the hyper-specific how to do it on your actual cluster hardware. Catalyst explores various physical implementations for the logic, generating multiple candidate plans before finally crowning the ultimate winner.
Joins are the perfect example to illustrate this. Catalyst pits different join strategies against each other. If the statistics show one of the tables is tiny, Catalyst instantly locks in the broadcast hash join, sending that small table to all nodes to completely bypass a heavy network shuffle. But if both tables are massive, it falls back to a robust sort merge join. The statistics drive the physical strategy.
But listen, there's a catch. This brilliantly optimized factory completely falls apart if Catalyst is making its decisions based on blind, outdated data. The engine needs fuel, and that fuel is accurate statistics. You absolutely have to actively collect these statistics by scanning your data using the Analyze Table command.
Which brings us to our final thought for today's explainer. Catalyst is an absolute master orchestrator, making your code brilliantly fast behind the scenes. But it is truly only as smart as the statistics you give it to work with. So you've got to ask yourself, when was the last time you ran Analyze Table on your massive datasets? It's a powerful reminder that while Spark is incredibly smart, you still hold the keys to unlocking this engine's true performance. Keep your stats fresh, stay curious, and keep exploring those execution plans. Thanks for joining us.